I like talking about randomness for many reasons, and the fundamental reason is that everybody I talk to and everybody I meet, including kids and people on the streets, have ideas about what it means, whether it's because of the luck or chance or notions of this type that are playing a role in their lives. Of course, for scientists, it's of all types, randomness is meaningful. Randomness in nature, randomness in mathematics, probability, entropy. These kind of notions are, occur and were thought about for millennia, really. And there are various definitions in different disciplines of what it means. And what I want to tell you about today is the meaning or the way we think about it in computer science, in computational complexity theory, which is my field, and how this differs from more traditional ways of thinking about randomness, and also what it means, what is the meaning of this notion, because it means it will have applications to things we actually want to do with computers. So the talk will have two parts, so let me tell you what they'll be. Even before that, so generally two parts that will somehow correspond to the power of randomness and then to the weakness of randomness. And we'll have to reconcile these two possibilities. Is it powerful or is it weak for computational purposes? And there will be some, so of course I realize that the backgrounds of people in this room is very, very broad. There will be nothing very technical, but there will be notions that maybe you didn't see. Some of them, it will not be so important to understand formally. In fact, nothing will be really important to understand formally. But if you have a question, just stop me and ask if you want to understand it better. So here's the plan of the talk. So I want to stress, especially for the scientists among you, randomness, probability exists in all sorts of domains. Here I'm going to talk about maybe the simplest kind. It's just discrete random events, and the most basic one is just a coin toss. You toss a coin and think about it landing on his head with probability 1/2 and on the tail with probability 1/2. And in fact, you have many of these. That many coin tosses independent from each other will be my basic model of perfect randomness. So just to test that we are all on the same page, if I show you two sequences, I will show you two sequences of 20 coin tosses, and you should tell me which is more likely to happen in this model. All right, good. So, perfect. Then you understand that, they are equally likely. That's a good thing to remember. So this kind of distributions, perfect coin tosses, are what we will think of as perfect randomness. Sometimes we say it's a uniform distribution on sequences. We say it's a distribution with full entropy. All are equivalent. And this will be our ideal thing. This will be the thing I'll show you is extremely powerful. And this will happen in lots of examples. Each one of these examples will be on one page, so if you didn't fully understand it, that's okay. There'll be a context with the next slide. So I'll just demonstrate the power of having such a stream of perfectly independent random bits in various contexts. And then we'll ask ourselves, is it, all these applications, all this power, is it real? Is it real in what sense? Do we actually have this kind of perfect randomness, and what to do otherwise? So in order to talk about that, we'll have to talk about what I call pseudorandomness. And this is a vague definition, and we'll make it better later. But generally speaking, pseudorandomness, you should think of it the study of deterministic structures, things with no randomness at all, but they share some common properties with random structures. And we'll I'll give you examples and applications of these. And after we are done with that, we'll be able to talk a bit more concretely about some of the things I mentioned in the abstract of the lecture, namely, what do you do if, if the world has no randomness at all? Or the world has some randomness, but not in the form of perfect coin tosses. How do we actually get the applications of perfect randomness without it? So we'll be able to say things about that. Okay, so I'll start. So I want to give these examples of the remarkable utility of randomness in various areas. And in each slide, you will see this. You have to think in the back of your mind just to remind you that for these applications, we need perfect randomness. And you can ask yourself, where is it coming from? That's what will come in the second part of the talk. Okay, so here's the perfect slide for post-election day. One of the oldest examples of the power of randomness is random sampling. And if you wanted to, this is a theoretical talk, so that's what should have happened with the polling. So here's this, I want to tell you about the theorem. I'm sure many of you know it, mathematical theorem. So what the mathematical theorem says. Suppose you want to estimate in a population of the United States, for example, some members of the population prefer red and some prefer blue. What is the statistics? What's the fraction of, let's say, reds in the population? Well, you can count them all. But one thing you can do is, for example, pick a completely random sample. So if you had perfect random bits, you can choose 2,000 of them. I picked this number, 2,000 of them, and just ask them whether they prefer red or blue. And then this remarkable theorem says that, which is called the law of large numbers, says that if the sample is completely random, maybe equally, we give equal weight to all subsets of size 2,000 in the population, then 99% of them, with probability 99%, the fraction we get in the sample and the fraction we get in the whole population differ by at most 2%. So it's a mathematical theorem, not too hard to prove. In fact, this theorem is stronger. This theorem does not depend at all. There's no, I think that this laser pointer doesn't work. Anyway, this theorem does not depend at all on the fact that there are 300 million people in America. The same result would hold true if we had this experiment done in China. Right? Just ask 2,000 people, the same things will be true. Or maybe if every star in the universe was, had an opinion, red or blue, it will still be the same. So it's an extremely powerful thing. Using perfect randomness, you can get very highly accurate information with extremely high probability, doing very little work. On the other hand, without randomness, if we wanted to know up to 2%, what is the statistics of this distribution, we would just have to go and ask maybe not 300 million people, but maybe just 2% less than that. Enormous amount of work. So there's a huge gap between what randomness buys you and what you could do without it. So that's the most simple and maybe the most ancient example of the use of randomness for, let's say, scientific purposes. I want to now give you more. Yes? Yes, it's independent of population size. If you pick at random 2,000 people from any size population, this theorem will hold true. Yes, it's the law of large numbers that depends only on the sample size, does not depend on the population size. It's very important. Yeah. So, yeah, there is no dependence in this theorem on the population size. That's a fact. It's actually not too hard to prove also.
It's got to be greater than 2,000.
Yeah, so these numbers, 99% and 2% depend on the 2,000, right? Actually, if you wanted 0.999% and you want the not 2% accuracy, but you wanted 0.2 accuracy, There'll be another number instead of 2,000, maybe 20,000, but again, it would not depend on the population size. More questions? Yeah, so perfectly random just means that of all the possible subsets of size 2,000, 99% of them will have this accuracy property. Okay, that's what it means. That's the definition there. So, and it's equivalent to say if I picked it uniformly at random, then it will have this property with probability 99%. Yeah. Okay. Everybody's happy. Good. So now I want to give you more sophisticated examples. Here's this is just one of many what we call probabilistic algorithms or randomized algorithms. A randomized algorithm is just a computer program that is using, besides whatever data, it's allowed to toss coins. It's allowed to use perfectly random bits. That's a probabilistic algorithm. So I'll give you an example of a probabilistic algorithm for a problem defined by a picture like this. What do you see here? There's some region in space. It doesn't have to be square. It can be any shape, any region in space, in the grid. And what you see in this picture is a particular domino tiling of this region, right? So you just divide it to dominoes, to boxes of size 2 by 1. Okay, that's one particular way to partition this shape into dominoes. Of course, there are many others, right? And the question is, how many are there? How many ways is there to tile this shape with dominoes? And this maybe seems like, because of the colors, maybe there's like a toy problem, but actually it's a fundamental problem in physics, or in chemistry, if you want. If you can do it, if you can estimate this number of tilings, then what you can do is, this captures really understanding properties of matters, of diatomic molecules, and it will compute for you various things that physicists are interested in, like free energy and probabilities of phase transitions and correlation decays and things that are important for actually generating things that are in your pocket, actually. So we would like to know this. So we would like to estimate the number of tilings of this shape. Now, there's a huge number of such tilings. So huge that if the shape is 100 by 100, counting it by hand, you will, the sun will burn out before you are done. So these people, Jerome Sinclair and Vigoda, devised a probabilistic algorithm, an algorithm to estimate this number that is using random coins that will finish the job in a second, if it's 100 by 100 or if it's 1,000 by 1,000. This is a very sophisticated algorithm. I'm not going to explain it. It relies on what's called the Monte Carlo method that was used initially by von Neumann and Ulam when they were studying the nuclear reactors, nuclear fusion. And so we can do that if we have perfect random bits. Now, if we don't, and you want to solve this problem, like I told you, the best known method is more or less trying them all. And that's impossible because of time. This will never end. But here I want to stress that this is only using the best known deterministic algorithm. So by deterministic, I mean no use of random bits. The best algorithms we know use exponential time, require exponential time, which for us, for all practical purposes, anything exponential is infinite. We can never do it. So there's a huge gap between, huge efficiency gap between what you can do with random bits and without random bits, as far as we know. And this is just one example of many, many other examples, because this, math and, math and physical science part of the foundation. I have here a bunch of other examples, mainly mathematical, of problems which have the same property. I don't have to I will not explain them, but they come from all areas of mathematics, generating large primes, factoring multivariate polynomials, approximating volumes of bodies in very high dimensions, computing large Fourier coefficients. All these problems, all you should, if you are not a mathematician, it doesn't matter, all you should know that they are extremely important. They come up in practice, and we really want to solve them on large input sizes. And the only way we can do that is using fast probabilistic algorithms that were developed for these purposes, sophisticated algorithms, which use random bits. And in that case, we can do it efficiently, quickly. And on the other hand, for all of them, and for many others, if there is no random bits, the best deterministic algorithms that we know of, require exponential time, which means that we can't really use them. Okay. That's another example. So there are many, many of these. So here the power of randomness seems extremely powerful. And that was sort of the feeling for several decades since they were introduced. I want to now switch to another type of application where randomness just doesn't make things much faster. It makes it possible where otherwise it's impossible. Here the setting is what's called distributed computation. This is a situation which you have in large networks, which are asynchronous. They have no common clock. So lots of agents talking to each other, trying to compute things or trying to achieve things. And these are just two particular examples of problems. I will, again, not define them, but I will tell you one nice thing about this field, as you can tell from the names of their problems and the pictures, is that they are good in making names for their mathematical problems. One is the dining philosopher's problem, which is really a problem about resource allocation and how to secure access to resources in distributed systems. And the other is called the Byzantine generals problem, which is a problem about coordination. I'm not defining them formally, but what you should pick up with your eye very simply in these two parts is that each has two theorems. One is a possibility result, the other is impossibility result. They say in both there are probabilistic algorithms to achieve whatever goals these goals are. There are probabilistic algorithms. So if the participants in these distributed systems can toss coins, they can achieve the properties, the desired properties. But if the programs cannot toss coins, they are deterministic, then it's impossible. It's just impossible. There's not a matter of time. It's just purely impossible to achieve. So here randomness buys you something that is impossible otherwise. Questions? Yes?
You talked about probabilistic and deterministic. How about pseudorandom?
We'll get to pseudorandom. But I already warned you and everybody else, pseudorandom is a word that people use freely without definition. We'll try to get definitions of this word. But yeah, later, yeah. Right now I'm just contrasting perfect randomness and determinism. It's a non-trivial proof. In each one of these cases, it requires work. It's a mathematical theorem that, amazingly, this theorem, there it's a combinatorial proof, if you want. Here, this proof requires topology. So, this question is very good, but it's not what I'm going to talk about now. I just wanted to contrast what happens when you have randomness and when you don't have randomness. All these theorems are not trivial, both the possibility results and the impossibility results. But again, I just want to stress that the problems themselves are very important in practical applications. They need to be solved. So it's really good that if we have randomness, that we can solve them. Yes? That's a great question, and there are no such examples. And you will see later, looking ahead, you'll see why. Okay. Now, The next two examples, I want to again illustrate the power of randomness, but not to achieve something, like in all these examples, but actually even to define something. Sometimes in order to make the correct definition, you can do it with randomness, cannot do it without. So let me give you two examples of this, two very important fields of science. So one is game theory. So first I want to tell you how game theorists define games. But strategic situation, I'll describe it by an example. This is an example of what's called the chicken game, defined by Aumann. This particular game is supposed to capture two maybe macho drivers driving in a collision course towards each other, and they each have two possible strategies. They can be, cautious and swerve to the side, seeing the lights of the other car. Okay, that's being cautious. Or they can drive on, hoping the other driver will swerve. And now, these possible strategies are denoted A and C, aggressive or cautious. And in the matrix that you see, which describes this game, are written the payoffs for the black player and the purple player. So the payoff, is the reward, which can be negative, is for every choice of the strategies they both had. So if the black is cautious and the purple is aggressive, the black gets 0 points and the aggressive gets 2 points. Like he proved himself more brave than the other guy or something. Anyway, so probably the AA entry should be minus infinity, I guess. But anyway, so that's the way game theorists describe a game. This is a very simple example. Games can have more than 2 strategies per player, so the matrix can be much bigger, and games can have more players. There can be more, this matrix can have more dimensions. There can be 100 players. And then you just have to describe what are the payoffs in every possible choice of strategy for every player. Yes? Yeah, so it's not it's just a story that goes with the matrix. What's important is the matrix. That's a mathematical description of the game. You can imagine a story. In fact, in most cases, this will define different games. So you can imagine 2 companies who are competing with each other and they are setting prices, right? And the question is what share of the market will buy their products. And analysts are trying to figure out what will be the meaning, the profits. But every such matrix of payoffs defines a game. No, what do you mean? They are not the same. In some, no, look in the, no, they don't. Look at the 0 and 2. They are not the same. So it just, what is the payoff for me and what is the payoff for you? The payoffs for you and me can be different. In this story, if I'm aggressive and you are cautious, I get 2 and you get nothing. In this case, it's just an example. You can fill it with any numbers you like. That will define another game that may have nothing to do with aggressive drivers. Yeah. And as I said, it can be a larger matrix and it can be many players. Okay? Excuse me? That's not the prisoner's dilemma, but the prisoner's dilemma is a perfect example of this. Yeah. You can capture the prisoner's dilemma this way and many, many other games you may have heard of. Battle of the Sexes is another one I like. Okay. So now here's a major question in game theory that was asked, in the early part of the 20th century. What is the rational behavior? So I give you the payoffs for every situation, for every choice of strategies. What should the players do? What will define a rational behavior? How do you just, what set of strategies is good for the players and what's not? And John Nash came up with this definition. which is he says rational behavior is stable behavior. Stable behavior is one in which, given the set of strategies, no single player has an incentive to deviate. Okay, so if the others are, doing what they are supposed to do, or what they, this set of strategies is given, if you know that the others are doing what is written there, you should not have an incentive to deviate. Okay, that's a stable situation. That's a definition. It's, in fact, the most important definition probably in game theory. It was done in 1950, but it's still a major solution concept in game theory. But Nash didn't get his Nobel Prize just for making up this definition. You can come up with lots of definitions. What was really important besides the definition is Nash's theorem. And the theorem says that every game, doesn't matter how many players, doesn't matter how many strategies every player has. It doesn't matter what numbers are written there inside this matrix or big multidimensional matrices, right? Doesn't matter. Every game has a Nash equilibrium. Every game has a stable rational behavior for the players to adopt, okay? That's what he proved. The point is that this theorem, that's not the end of the theorem. Such a stable solution, such a Nash equilibrium always exists if you allow players to have random coins. If they are allowed to mix, to pick their strategy at random. If this is true, then every game has a Nash equilibrium. So there is always a rational behavior for this. In this case of this particular game, there is a unique Nash equilibrium where you are cautious with probability 1/3 and aggressive with probability 1/4. Probably a simplest example I could have given is the stone, paper, scissors example where you all rock, paper, scissors, where there's only one stable strategy, you pick with probability 1/3 each of them. Otherwise, the other guy has an advantage. Anyway, there's always a solution in random strategies, but there are many, many games where if you restrict, in fact, this is a particular example, if you don't have randomness, then there is no rational behavior of this sort. So here randomness is absolutely essential just to define this notion. Okay, so it's another aspect of the usefulness, utility of randomness. A very, something that's much more important in your lives is cryptography and electronic commerce. In this field that we literally use every day, without randomness, you couldn't even make the first step. The first step is just defining the notion of a secret. So secrets don't exist if you don't have randomness. This was already defined, formulated by Shannon when he defined his information theory and entropy, saying more or less informally as follows. I mean, a secret is just as good as the amount of randomness it has. Okay, if you pick your, let's say, password as a, let's say a 9-digit password by just picking it uniformly at random, so every digit is has 1/10 probability of every value, then my chances of guessing it is 1/1,000,000,000, 1/10 to the power 9, right? And this randomness is essential there. If you, on the other hand, pick your password just as a, phone number of one of your friends, maybe you have 20 or 50, or maybe you have, I don't know, Facebook friends, so you have 500, then my chances of guessing it is, 1 in 500 as opposed to 1 in a billion, right? So it really depends. The amount of randomness you invest in generating your passwords is essential for its, undecipherability. And if you don't have any random bits, and I know what you're doing, then I can guess it for sure. And randomness is then essential for anything, so I'm not going to go over these important primitives of cryptography that, again, many of them you're using without your knowledge, or your computers are using, all require randomness. Without randomness, they are meaningless. So it's essential for the theory of cryptography. Okay, so that was another example. And there are many more examples. This is another one I like very much. I mean, we sort of think that randomness goes into these procedures, especially when we bet on something. And this is really a place where you should wonder where the random bits are coming from. So far we talked about the power of randomness for many different applications and theories. So good. So now we are going to address this function, this question of where the random bits are coming from. Okay. I don't know about you, but when I don't know the answer to a question, I just ask Google. So I'm sure that I know many people who do the same, because what would you do? I mean, especially if it's a hard problem. It usually doesn't have good answers when I want to prove a theorem, but this kind of question, where would you, suppose you wanted perfect random bits, where would you get them? So, okay, I asked Google, where do you get them? I asked true random bits. And actually, the answer is not surprising. There were 4 million answers, and they are not surprising in that, where do you get them? You buy them. Like anything else that's useful, you have to pay for it. So this is what the outcomes here, if you go and check, there are names of companies that actually sell you random bits for money, or sell you things that promise to generate random bits. And then you click on them to study, well, where do they get their random bits, right? Okay, well, in some places, they get it from radioactive decay. They tell you. Other from atmospheric noise. These two get it from quantum phenomena. In other words, they get it from various physical sources. The most, actually, you should wonder. I mean, I certainly wondered if anybody is actually buying random bits. So these guys, this company is selling this cheap. And this is actually, people buy it, I think, maybe for $1,000 each. Their main customers are casinos. So, of course, you can wonder about what goes inside the chip, and is it working? Does it actually produce random bits? And there's a really interesting work on that I will not get to. Okay, but basically, it seems to be that there are people promise that there are sources of bits that are random. And the question is, how do you check that? And how do you define it? Even when is it random, or maybe it's random for you, or random enough, or how do you know? So in order for that, we need some definition. Okay, so the next slide is the most important slide in this lecture, right? If you remember this, you understood what the message is, then you understand what is the computer science complexity theoretic take on the meaning of randomness, and how to this meaning is taken into ways of actually generating it even when you don't have it. This paradoxical thing. So I want to define it, and I need a victim. So I need a volunteer. Anybody? You want to volunteer? You don't? No, you don't have to get up. I'm not going to cut you in half or anything. No, you just have to answer 3 questions. Okay. So, okay, good. So I need a coin. This is a coin. And so this is me here, and that's you. So what you're supposed to do, I'm going to toss the coin. And just as it leaves my finger, you should guess what it will land on when it is on the floor. Heads or tails, okay? Okay, actually, I'm not actually going to toss it. I just want you to estimate what will be your chances of guessing it right, okay? So my first question, what do you think your chance, again, I'm tossing it, it just left my finger, and then you have to say heads or tails before it hits the floor. what do you think is the chances that you'll get it right? Yeah? Okay, good. You should clap hands or something. No. Okay, yeah, that's what everybody would answer, and that's what I would answer. That makes perfect sense. So good. So let's change the experiment, okay? The experiment changes by now I give you a laptop, okay? It sits in your lap, and now I ask you the same question. You should guess what it will come up after I toss it before it hits the floor. What do you think the chances you'll get it right?
Sorry, what am I doing with this laptop?
Whatever you want. It's your laptop, not mine.
Let's see how the laptop helps. Go on.
Okay, good. Very good. I mean, see, it's not that scary. Okay, good. That's what I think, and that's what most people will answer. And okay, good. So let's change the experiment once more. And in this, I should say, this experiment is from this really amazing paper from '81 by Blam and Micali. The new experiment is now beside your laptop. I give you a bunch of video cameras, all trained on my finger, and they're all connected to a Cray supercomputer, which is connected to your laptop. And you can pre-program it to do whatever you like. And now as the coin leaves my finger, you should guess what it will be when it lands on the floor. What do you think is your chances of getting it now? All right. You know, I paid him beforehand, so it's no. Yeah, again, I think most people will answer this because, you know, it's a simple physical process. If, you know, you could probably calculate the spin, the angular momentum, the distance to the floor, the humidity in the air, whatever determines this event, and then, you know, you would know exactly, or almost surely what it will be when it lands on the floor. Okay, so what's the point? What's the point? Well, the point is that this random event, right, the predictability of the outcome of this experiment, this was the random event, didn't change. In all three stories, I was doing the same thing. The random phenomena was the same, coin toss, right? What changed? What changed was the observer, or really the computational power of the observer, right? So the meaning of this story I told you is that to appreciate randomness, to define randomness in a way that's useful, certainly useful in computational settings, what you really need to do is to understand the computational power of the observer. The more power they have, the less unpredictable this thing looks like, so the less random it is. Randomness, so this is a completely different than all historical definitions of randomness which depended on the phenomena which were objective. This is a subjective definition, and it's an operative definition. It's critical to the understanding of the consequences of this theory. Questions? Yeah, no. Very good. So we will, yeah, I mean, I can answer this now, I can answer this later. But let me, okay, so the question was quantum you know, measurements of, let's say, of spins of photons. They are random, they are unpredictable regardless of the, or so you believe, regardless of the power of the, yeah. So that would be okay because maybe the answers in that story won't change, but I just want to point something out, and that there is a big difference between what quantum theory promises us, and that's what it promised. So there's a mathematical theory called quantum mechanics, which predicts that if you measure the spin of a photon that's generated by some device, it will be like a completely unbiased coin, no matter what, how powerful you are. And that's the theory side. And then there is a device, like my finger, which is generating this, the apparatus for measuring and so on. That's some physical device which I'm willing to bet does not do exactly what the theory does. Somebody built it, okay? And then it's not. And then maybe the computational power will change. But all I'm saying is, for some, phenomena that you don't change them, you change only the observer, the unpredictability changes. And that's the only message I want to convey. Okay, so what can be done with this? Okay, so I want to, before that, tell you about pseudorandomness. I'm going much slower than I should, or than I hoped for. That's okay. We don't have to reach the end as long as you understand everything I'm saying. I want to talk about pseudorandomness, which is what you get to define after you realize that the power of the observer over the set of capabilities of testing that the observer has lead to. So what is pseudorandomness? I said before, is a study of deterministic structures that have, these structures can be lots of different things. They can be functions, they can be numbers, they can be graphs, they can be various objects. So you have a collection of objects and you want to know whether one of them is, you want to call it, whether you can call it pseudorandom. So this slide is a bit abstract, but I'll give you an example in a second, or in fact, several examples in a second, okay? So you have this universe of structures, and what we will call a pseudorandom or random-like property, so it's a property, it's a subset of the universe, is simply anything that occupies almost the whole space. Or again, a random-like or pseudo-random property is something that is shared by almost all elements in the space. Why do we call it pseudo-random? Because if it takes almost the whole space and you pick an element at random from the universe, purely uniformly at random from the space, then it will have this property with high probability. So that's why we call it. It's a name. And this name depends. There can be many different pseudo-random properties, and I'll give you examples. And, yeah.
When you say almost all, that means the complement is a measure zero?
Measure zero if it's continuous, or maybe it's 99%. Yeah, if it's discrete. Okay. So these properties will relate to what observers are testing. It will be like a test. Anyway, what I want to, important message I want to convey is that both mathematicians and computer scientists are studying pseudo-random properties of this sort all the time. They are somewhat different questions. Mathematicians typically want to know, and you'll see an example in a second, whether particular natural objects have a particular pseudo-random property. Whereas computer science people would typically like to just be able to find one efficiently, just find an element with a property, some special kind of network or special type of code or and so on. And the good thing is, and so they want just to, as opposed to asking whether a particular element has this property, want to find an element with this property, which has a very cute phrasing by Howard Karloff. He calls it finding hay in a haystack. You're looking at a pile of hay. Almost everything is hay, but there's a danger that you'll start picking things and they'll all be needles. You want to avoid that. So even finding hay in a haystack can be hard if the hay is exponentially large. Anyway, but there's two points of view are very, there's a lot of interaction between mathematicians and computer scientists on these type of questions, and I'll show you some examples. So let me first just start with one pseudo-random property so that you have at least one concrete example, and then I'll do a couple more. Okay, so everybody recognizes this number. Good. It's an infinite decimal. And I want to define normal numbers, okay? Normal numbers will be a property of such infinite decimals. And normal numbers are defined by a sequence of conditions. So what are the conditions? Conditions about this infinite expansion. I want that every digit, like 7, will appear 1/10 of the time, like it would in a random sequence. Okay, I want that every pair of digits, like 5, 4, will appear 1/100th of the time, as it would in a random sequence. I want that every triple will appear 1,000th of the time, et cetera, for every finite length. That's an infinite number of conditions. I want them all to be satisfied, but that's not all. I want the same conditions to be satisfied in every base. If you write this number in base 2, I want every digit to be 1/2, blah, blah, blah. So in base 2, base 3, base 25, base 1,000,000, okay? If a number satisfies all these countably many conditions, I call it normal. And now you should wonder, are there normal numbers? In fact, it's a simple theorem of Borel that almost all numbers, all but measure 0, of the real numbers are normal. So this property is abundant, and we said a large property, abundant property, I want to call pseudorandom. So that's a pseudorandom property. That's your example. And now you can ask the questions I mentioned before, whether particular numbers are normal. So is pi normal? Turns out it's an open question. Nobody knows whether pi has this property, or whether e does, or square root of 2, we don't know. That's an open question. There's a little more knowledge about finding whatever, this has to be defined, efficiently finding such numbers. But anyway, you can see a pseudorandom property and these kind of questions coming up with respect to it. Now, normal numbers, I must tell you, are not the most sought after problem in mathematics. People think about it, but it's not like a major problem. So now I want to show you that absolutely major problems in mathematics and in computer science are questions about pseudorandomness. So it brings the question of what's a major problem. I like to do it when there are many students around, because they have to pick problems for their, PhD thesis or something like that. And, how do you know that the problem is important, is major? Anybody has any suggestion? Well, obviously the answer is money. Problem has to have a large price on it, and then it's important. At least, well, anyway, even if you don't buy this, this particular list is a list. It's called the Clay Millennium Problems. This was a list of 7 problems that a bunch of famous mathematicians set at the request of the Clay Foundation to pick out of all problems in mathematics the problems that are really important for the next century to work on. And they came up with these 7 problems. So if some problems from this list are pseudorandomness questions, then maybe we are happy. And if you want to make $1 million, you should start quickly, because one is gone. But even though it didn't take the money, right? But I want to show you that these 2 problems, so 2 of these 7 problems are problems about pseudorandomness. And if you told it even to people in these fields that these are problems about pseudorandomness, it would not be obvious. So I want to show you that. So I'm not going to explain why the P versus, by the way, I'm just curious in this audience, how many people heard about the P versus NP problem? Very good. So most people, and I'll just say, yes? Because they didn't put it in. What do you mean? This list is a formal list. No, they don't have it there. But they have it in other lists, not in this list. But I could have put it, but it's not. I don't want to talk about it also. I want to talk about problems that have, yeah. But anyway, in this list, that's a famous, fixed, well-defined list. It doesn't exist.
When was this list?
2000, the year the millennium. It's called the millennium because the year 2000. It was sort of to imitate what Hilbert did in the year 1900. Yeah. The P versus NP is the most important problem in computer science. It is a problem about pseudo-randomness, but I'm not going to define why it's written here. But what I want to tell you is maybe the most famous, and some people will say the most important, I don't know, problem in mathematics, the Riemann hypothesis, is also a problem about pseudorandomness. This I will explain in more detail in a second. I just wonder how many people in the audience can formally define the Riemann hypothesis. Not bad. So good. So all the others, don't worry, because in 5 minutes, you will all be able to formally define the Riemann hypothesis. Not only will you be able to do it, you will be able to go home and explain it to your kids and your friends and everybody else. Because it's a simple problem to state, maybe not to solve, but to state, if you think of it from the pseudo-random viewpoint. Okay? So let me explain the Riemann hypothesis. So in order to understand the Riemann hypothesis, you have to understand about the random walk or the drunkard walk. What's the drunkard walk? So imagine this is a street, and here in point 0, there is a pub. And you should imagine somebody going to the pub, has a few beers to drink, coming out to the street, and starts walking up and down the street. Okay? And being somewhat drunk, it maybe goes, one step up or one step down with probability half. That's the behavior that we postulate, okay? 1/2 probability step up, 1 probability step down. And then you can wonder what happens to this guy after he walks, let's say, for 100 steps. Where is he? Okay, so I ran here, I really stole, I didn't. I stole this picture. What it depicts is running this process 10 times, so there are 10 colors here, and it shows you the steps that this person could walk, in the red one, in the blue one. And what's remarkable about this picture, if you haven't seen it, this kind of things before, is despite the fact that the guy walked 100 steps, he remains within 10 or 15 paces from the pub. So right, he walked 100 steps, but he's quite close to where he started from, okay? And in fact, this phenomena is very simple to observe and prove. In fact, almost surely, so for almost every walk, out of all the possible walks you can take, for a random walk, after n steps, you will be within roughly square root n from the pub, okay? This is a fact that holds true for almost all possible walks that this guy might take, okay? And that's great because when we see a phenomenon like that, again, it's a pseudo-random property. Staying close to the origin for a walk means that it happens almost all the time. That's a pseudo-random property. And now we can ask similar questions like before. Is a particular walk, which we can define, has a property? Like we asked whether pi is normal, we are going to ask whether a particular walk that I'll define for you is sort of homebound, stays close to the origin. Okay, so let me define for you a particular walk called the Mobius walk, okay? To define the Mobius walk, I want to define the following. For an integer x, p of x is just the number of different prime divisors of x. And given that, I'm going to define the Mobius function, mu of x. It's going to be 0 if the number is divisible twice by the same prime. Maybe it's divisible by some square. But otherwise, it's either +1 or -1. +1 if the number of prime divisors is even, -1 if it's odd. Okay, so it's a well-defined function of integers. But because it's a well-defined function of integers, it defines a walk. Write down the integers, just these are the time slots, right? What the person does in time 1, 2, 3, 4, 5. Let's say it behaves according to the Mobius function. So it's slightly different than before. There is a possibility that it stays in place or goes up the street or goes down the street. But it's a well-defined walk. And you can ask yourself, does this walk have this particular pseudo-random property? If he walks for n steps, will he be within square root n of the origin or not? That's the question. And here's a remarkable theorem. This walk has this homebound property. It stays close to the origin. For every n, it's within roughly square root n of the origin. And the equivalent condition is the Riemann hypothesis. So just the question of whether this particular very simply defined walk staying close to the origin is equivalent to the Riemann hypothesis. It's a formulation, it's a formal formulation of the Riemann hypothesis. If you want to prove the Riemann hypothesis, just prove this property, that this work stays close to the origin. Okay? So this is an indirect way of showing the power of this point of view about pseudo-randomness and its position in math and computer science. These are just examples. I could give you numerous other examples where classical questions in various areas of mathematics and computer science can be phrased in this pseudo-random questions about pseudo-randomness. This may not be the best way to solve it, or maybe it is, I don't know, but it's just formulating it. Okay, so I want to tell you about the consequence of this point of view. I'm not going to explain how this point of view actually gives what I will show you, but I at least want to tell you about the consequences of this subjective definition of randomness and the use of particular pseudo-random properties, not the ones I showed you, but other ones. What they tell us about coping with the lack of randomness, or the lack of perfect randomness, how does it affect all these applications we saw in the first part of the talk? Okay. These are consequences of major developments in complexity theory in the past 3 decades, this understanding that I'm going to summarize just on one slide. Okay. I want to think about 3 possible worlds. The first one is the one we started with, a world where we have an unbounded number of independent perfect random coins. This is what we assumed for all the applications in the beginning. The second one is one in which maybe we don't have that, but maybe physical phenomena have some entropy in them, maybe measuring photons or sunspots or stock market behavior or something like this. These are phenomena, physical phenomena that has some randomness in that, but not in perfect form, just weak sources of randomness. Can this be used? And finally, a world which is completely deterministic. Nothing is random, everything is predictable. And in all these cases, you want to know what happens to all the applications we talked about in the beginning. So here we, okay, if you have perfect randomness, we saw lots of applications. What survives if you don't have it? And it turns out that these 2 theories that I'll tell you about tell us what can be done in those 2 possibilities. In the case that there is weak sources of randomness is something you formulate. Everything that was algorithmic in the first part of the lecture, so all these probabilistic algorithms, sampling, and things of that I talked about in the beginning can be carried out without perfect randomness, just with very weak sources of randomness. It's clear that you cannot just take the weather measurements and plug it into your algorithms. You have to do something much more sophisticated because it's not clear where the entropy is. But in this, extractor theory, which gives this result, you are able. There are deterministic algorithms that, again, are complex, and I will not define them, but they are able to take very weak sources of randomness, regardless of who generated and how they were generated. Maybe we don't understand, where the entropy hides in stock market fluctuations or internet traffic. Regardless of how they are generated, as long as there is some entropy there, it can be extracted deterministically from this random samples. And using this, you can use them in all the algorithms. So that's one theory that's called the extractor theory. And in this one, we still are using some randomness that we hypothesize exists in the world. The more challenging, well, this was challenging, but another challenging question is, what happens to all these applications of perfect randomness if simply there's no meaning to coin tosses? We always know what it lands on, okay? It turns out that even in this case, almost all the applications that we want to have, we do have. So I want to say what this result a bit more formally. So I gave you again at the beginning a list of probabilistic algorithms, and that goes back to a question that was asked here. A list of efficient probabilistic algorithms for which we don't know any sub-exponential deterministic algorithm. We don't know. So what happens here is that under an assumption, and this is important, under an assumption, what assumption? Assumption like P is different than NP. Maybe I didn't, maybe I should have said a word about this. What this question or challenge of P versus NP is simply the question of whether there is any computational problem of the type anybody would like to solve that's actually hard. So since lots of things we want to do seem hard, that seems like a safe bet. Most people believe that P is different than NP. Most people believe, let's say, that the traveling salesman problem or satisfiability problem or lots of, or even factoring integers are hard problems. So let's believe it for a second. We believe that one of these problems is difficult to compute. Under this assumption, it turns out that randomness is not needed at all in probabilistic algorithms. So that's the main message here. Every one of these efficient probabilistic algorithms that we saw before, and many that we didn't see, can be replaced by another one, which is completely deterministic, does the same thing, never makes an error, and runs almost as fast as the original one. So again, if this so-called the hardness versus randomness paradigm, if we have some problem, some computational problem that is hard, as we believe, then that's all you need. You can use it somehow to replace random bits in your algorithms with deterministic bits that nevertheless fool your algorithm into behaving just as it did when it had random bits. So it's an optimistic message, those two. You don't need much. All these applications will exist essentially even without perfect randomness. So I'm out of time, and I will not tell you, I'll just put my last slide. I will not tell you how these are done. I'll just say that they all use various notions of pseudorandomness. And I'll put my last slide here, and this I will not, I guess, just a summary slide. Oops, lots of nice things. Yeah, so just summarizing, this I think is very important to remember this definition of randomness that we have, which is a subjective definition. That's the take that complexity theory takes on randomness. Pseudorandomness is a family of definitions, and it captures lots of problems both in math and in computer science. The message of the previous slide is that lots of applications of randomness survive even in a world which has very weak randomness or no randomness at all. And finally, these pseudorandom objects that I did not really talk about turns out to have, these are really important in lots of other applications, even if you don't need randomness at all. They give you error-correcting codes, they give you robust networks, and many other things. So they are really important on their own. Thank you.